Hi there. So we're going to get into chapter 12, which is covering the structures and properties of ceramics. Now, for the last 60 years, really common materials were china, porcelain, bricks, tile, glasses. But now there's a greater understanding and a larger number of materials that fall into this class, including some of the carbon materials that we'll talk about later, more advanced materials, nanomaterials. But with a nod to the traditional ceramics, fun fact is ceramics comes from the Greek word keramikos, which means burnt stuff, which is a nod to how ceramics are traditionally made, and that you take a clay or something that you've mined, you fire it in a hot oven or fire, and then that causes the properties of the material to change from sort of mushy and malleable to a hard, glassy type substance. Now, for the atomic bonding in ceramics, most of it's ionic in character. For those who have a large difference in the electronegativity, like a calcium fluoride, and then you have a large ionic character, as we discussed earlier in this semester. However, there are some ceramics made of things like carbon and silicon, which have small differences in electronegativities and have therefore a larger percent covalent character. However, most are ionic in character. The first type of structure that we're going to talk about for ceramics are the class of structures known as the oxide structures. And the typical kind of thinking about these is that you have these oxygen anions, which are larger than the metal cations. For example, magnesium oxide, aluminum oxide, silicon oxide type structures fall into these classes. Now, if you have trouble remembering, like I do, which is the cation and which is the anion, the cation is the one with the positive charge to it once it's been ionized. And I remember that because it's got the plus sign for the positive and it looks like the T in the word cation. So that's how I remember it. So if you, like me, have trouble with 50-50 questions, there's a little mnemonic for you. It might puzzle you a little bit as to why the oxygen anion would be larger than the metal cation, since the metal cation typically has a larger larger molecular weight to it. And the reason for that is that the anions are usually larger because the cations give up their electrons. And then what that happens is you form a positive atomic core, that nucleus, and there's less screening, and so it pulls those electrons in tighter to the nucleus, making the radius smaller. For example, iron that has a charge of 2 plus has a radius of 0.077 nanometers, whereas iron that has a charge of 3 plus has a smaller radius of 0.069 nanometers. So that's significantly smaller and helps emphasize the point. Now, there's different factors that determine the crystalline structure. One of those is the relative sizes of the cations to the anions. What's the ratio of the radius from the cation to the anion? You're going to get a formation of a stable structure when you maximize the number of oppositely charged neighbors. Of course, that makes sense because light charges repel for the Coulomb force, and they don't want to sit next to each other. So it's going to be energetically favorable to have positive alternating with negative as much as possible. You're going to have more stable structures when your positive and your negative charges touch. This is, of course, using the idea of a hard sphere model for atoms, where they're modeled as spheres that actually touch one another rather than the messy truth, the more messy truth. But for that, you're going to have stable structures when they touch like this, whereas if your cation is a tiny little guy in the middle there, that's going to be less stable because then that would force these negative charges here to touch, which they don't want to do. Also, a thing that dictates what the structure is the maintenance of charge neutrality in the chemical formula. So, for example, calcium fluoride here, you have 2 fluorine atoms for every calcium, and if that were a different ratio, if, for example, there were 1 fluorine atom for every calcium, you can understand that that would greatly impact what structures would result. Each unit cell has to have a neutral charge to it, okay? So if each unit cell has to have a neutral charge, then when you pack in different numbers of cations and anions, and that forces the crystal structure to change. Your coordination number is going to change. Remember, the coordination number is the number of nearest neighbors that things have. So for example, for a cation, you have to have a certain number of anions as its nearest neighbor. So your coordination number is going to increase with the ratio of the cation to the anion radii. And to form a stable structure, you need to figure out how many anions are going to be surrounding that particular cation or positive charge. So as the ratio or the radius changes, that changes the geometry of the system. It's actually very, very, very dependent upon the geometry, and it's not really super difficult to figure out what the minimum value for this radius ratio of the radii are, as I'll show you in just a second. But to define what these ratios are, if the ratio of the cation to the anion radius is less than 0.155, then you've got a coordination number of 2 in sort of a linear structure. If it falls between 0.155 and 0.255, you've got a coordination number of 3 and you've got a triangular structure. As it increases, though, from 0.225 to 0.414, you have a tetrahedral structure, and then you get this zinc blende looking crystal like you have over here. And then if it goes from 0.414 to 0.732, you have an octahedral structure, and that results in structures that look like this sodium chloride or rock salt structure over here. 0.732 to 1, you've got a cubic structure, and that gives you kind of the cesium chloride structure that you see here on the bottom. Now, the most common coordination numbers for ceramics are 4, 6, and 8, resulting in the zinc blende, sodium chloride, and cesium chloride structures that are shown here. Now, to emphasize how simple geometry dictates this, I'm going to do this example problem for you. And this is a computation of the minimum cation to anion radius ratio for a coordination number of 6. Remember, a coordination number of 6 fell within this range for the ratio of the radii, 0.414 to 0.732, and that led to the octahedral structure that you see here. Now, for the minimum ratio, what's going to happen is that your cation here, shown in red, is going to be perfectly touching at the minimum configuration all of your anions here, which means that these anions aren't going to get pushed out and away from each other. They're still going to touch on the edges like this. They're not going to be shoved out, and that will give you your minimum, okay? Now, the unit cell, remember, is the smallest cell that you can construct. And so the unit cell dimension is going to be connecting center to center these anion atoms here, okay? So it's going to be connecting that center to center. So it forms this little structure right here. So in that case, you have a square, okay? You have a square when they're touching because it's not bulging out or anything. And the square, the sides of the square, is going to equal to 2 times the radius of your anion, because in the hard sphere model, these anions would then be touching one another. And so this is 2r for your anion right there. Now, what you want is the ratio of the radius of the anion to the cation. So you need some kind of expression which has both the anion and cation radius in it. So to do that, we're going to go across the diagonal of our little square like so. Then I can write an equation which relates 2 times the radius of the anion. So you can see that you have 2 green atom radii in there, and then 2 red atom radii right there, and that equals to the square root of 2 times your unit cell size, and that's because it's going across the diagonal of my little square, which gives me the root 2a for that length. Okay, now what we want to do is we want a ratio of the cation to anion radius, so we want to get rid of our a here. We want to get rid of that, and we can do that by relating 2 times the radius of the anion to our unit cell size, a. Okay, and then we plug that back in for a, and we end up with this expression here: 2r anion plus 2r cation equals 2 root 2r anion. And then it's just a little bit of simple algebra to express that as a ratio of a cation to an anion radius. And when you do that, you get r cation over r anion equals root 2 minus 1, which is 0.414, which, sure enough, is the very minimum for that range for your octahedral site. Okay, so what you would do geometrically then is you would figure out what the minimum is for each range, for each structure, okay, which you could do geometrically just as simply as I did here for the octahedral structure. And then, of course, the range for the previous one would go up to the minimum of the next structure. Okay, so that's how it's done and that's how it's dictated. Now, given these ranges, we can predict the structure, crystalline structure of different materials. So, for example, for iron oxide, on the basis of the radii, what crystal structure would you predict for iron oxide? Okay, well, first you have to look at the chemical formula. So this is FeO. Now, when oxygen forms an anion, it loses, it gains 2 electrons. So you've got O2 minus, okay? Now, iron has a choice. It could be 2 plus or 3 plus, but in order to have just one iron with the oxygen, then you've got to choose the 2 plus. Okay, so that dictates what the radius is, and there's a table of atomic radii that you have in your book. So there's your 2 atomic radii. You construct your ratio, 0.077 over 0.14, and you get a value of 0.55. Now, because that falls in the range of 0.414 to 0.732, then you know that the coordination number is 6, and you've got your rock salt crystal structure. Another example of that one is, let's figure out what it is for cesium iodide, okay? So if you go to your table 12.3, and you look up the radius for cesium and the radius for iodine, then you get 0.17 and 0.22. And so if you construct that ratio, 0.17 over 0.22 is 0.77, and so that gives a coordination number of 8, and you have your cubic structure, okay? Another thing that can affect the structure of ceramics is bond hybridization. Now, what is bond hybridization? Well, what happens is you have your electron clouds, right? We talked about the structure, for example, of the hydrogen atom and the orbitals that result out of it, the S, the sort of spherical orbitals, the P, the dumbbell shapes, the Ds, and so on and so forth. But if you think about it, let's say that you have those kinds of shapes in your bonding structures. What can happen is the electron clouds can actually overlap with each other. And when they do that, they form a new sort of sum shape or a hybrid orbital that has a shape and structure all its own, okay? And this is known as bond hybridization. This only happens with covalent bonds, and so what that means is that the bonds are very directional, and because the bonds are directional, that dictates where certain atoms are going to sit, because they're forced to sit in certain places with respect to other atoms, and that dictates the crystal structure. So you see it a lot with covalently bonded materials, like, for example, silicon-carbon ceramics, and they are going to have a very low percent ionic character, a high percent covalent character, and then bond hybridization can really affect the structure of these materials. Now, bond hybridization is kind of a complex topic, and so what I'm going to do is I'm going to require you to watch the Crash Course Chemistry lecture on bond hybridization that's underneath. The link to this is underneath the link to this online lecture on our course website, so please watch that. Going over some of the common structures that you'll see in ceramics, when you have one cation and one anion, that forms an AX crystal structure. There's different kinds of those. One example of that is the rock salt or sodium chloride crystal structure that you see here, okay? So what you see here is you have your sodium cation and your chlorine anion, and if you look at the structure, it really looks like your chlorine here, your anion, is forming an FCC structure. Now we don't call it an FCC structure, okay? The reason we don't call it that is because it's not a pure thing. It's not all chlorine, okay? It's got sodium in there too. But what it really looks like is 2 FCC structures. If you were to move over, for example, and put the sodium at the center of the face, then it would look like a perfect little FCC structure there. So what it really looks like is 2 FCC structures kind of interlocked with one another, okay? Other examples of the sodium chloride structure are magnesium oxide and iron oxide. They also have this typical sodium chloride structure. Okay, another type of AX crystal structure is the cesium chloride structure. So for this one, it looks a lot like a BCC lattice. Now we don't call it that, okay, because here your chlorines are sitting on the corners and your cesium is centered in the middle there. So it's a blend, so we don't call it a BCC structure, but it looks a lot like the BCC structures that we discussed way back in chapter 3. Now they can get more complicated, and they get more complicated the more complicated the chemical formula is. Then the structures get more and more complicated and the unit cells get bigger. Here we see the fluorite structure, which is calcium fluorite, and you have 2 fluorine atoms for every calcium. And then you end up with this kind of structure here. Of course, you have a lot more of the fluorines, which are in the green here, than the calciums. And you can see that if you look very carefully, you can see that the heights of these calciums are a little staggered, so it's not perfectly BCC. Here's your perovskite structure. This is when now you have 3 constituents. Here you have titanium, barium, and oxygen mixed together into a structure, and this is just crazy cuckoo. Here you have one of them kind of in a simple cubic looking thing on the corners. The other one takes the face-centered sides, and then the other is straight there in the middle, in the middle of the body. So you can see it gets more and more complex as you add more constituents into your ceramic. If you have trouble visualizing any of these crystal structures, because I know I do, then there's software out there associated with your textbook that you can look at, and you can look at some of these things, rotate them around in 3D, and play with it that way. And I encourage you to do that. Now, since we are talking about crystalline structures, you can actually calculate theoretical densities for the ceramics based upon it. Of course, with defects and things, the real density will be lower than the theoretical, but it does give you a target value. The formula associated with density computation, your density rho, is equal to n prime. N is equal to the number of formula units per unit cell. And then you multiply that times the sum of the atomic weights of your cations and your anions, okay? And you divide by the volume of a cell and Avogadro's number. I'll do an example for you now because an example is worth a million words. Here we go. Magnesium oxide has a rock salt crystal structure and a density of 3.58 grams per cubic centimeter. So determine the unit cell edge length. Well, here's what you do. You look at this, and you're going to plug and chug into that formula. Rho is equal to n prime times the sum of your atomic weights divided by the volume of the cell divided by Avogadro's number. All right, so first of all, we need to determine what n prime is. That's the number of pairs or number of formula units that are in here. Now, what I did here is just look at the anions, the green here, and count the total number. All right, so here I'm looking at just the green. If I look at the ones on the corners, okay, there's my corners, and I know that there's 8 corners in a cube, so there's 8 of those, and I know that each corner atom is only going to be sliced so that inside the unit cell I only have 1/8 of each atom. So 1/8 for each atom times 8 corners, and I have 1 anion. All right, now, they're also centered in each one of these faces, okay? Centered in each one of the faces. Now, there's 6 faces to a cube. And I know that when it's centered in the face like that, the atom basically gets sliced in half by the unit cell. So 6 times a half gives me 3. And then 1 plus 3 gives me 4. So there's 4 total anions in there. Now, because it has to have a balanced chemical formula and you have to have a unit cell having the same neutral charge, then I know that if there's 4 anions, there have to be 4 cations, so there have to be 4 pairs. All right, so 4 pairs are possible. So n prime is equal to 4. Now, I would also look up on the periodic table what the atomic weights are for the constituents of the formula. So I have magnesium. Looking out the periodic table, I get 24.305 grams per mole for magnesium and 16 grams per mole for oxygen. Okay, so I'm going to sum that up inside my formula. So I have 4 times 24.305 plus 16, and then I'm going to divide by the volume of my unit cell, which is A cubed, and then divide by my Avogadro's number there. When I do that and set it equal to the density, which is 3.58, I can then solve for A. And when I solve for A, I get 4.2 times 10 to the minus 8 centimeters for the size there. And that's going to end up being, of course, 0.42 angstroms for my unit cell length. Okay, I hope that helps. Hope you found it interesting, and let me know if you have any questions.